Alright, so just picking up where I left off, the conclusions, here's what I want you to think about. So just in terms of number 2, overlapping at 1 dot, if you have two Sona, say they're monolinear, the idea of overlapping at 1 dot, we can think of this as like an in-between step. Imagine you had two Sona that were monolinear, and you just stretched, as I've been talking about in these videos, stretch one part of the path to encapsulate this entire other loose Sona, and then you return back to where you started. Because this black part is all one path, and this black part is all one path, then breaking here and tracing all of this and then returning is still one path. And then if you imagine kind of pushing these things together until these two dots line up in one place, like up here, that's why this is monolinear. This is why this remains bilinear, or in this case ends up being trilinear. Ends up having, doesn't reduce the number of curves. This case of overlapping by 2, we'll talk about that later. It's more complicated. The point of having number 3 in this group work was for you to see that there are consequences. Overlapping by 1 or by 2 can be surprising. It might keep things monolinear. It might reduce the number of curves, where this increase the number of curves. Just to give you a sense of the complexity. Now the second part of the group work here involves squares, and this is something we're going to look at, and I think it's there's an understandable theorem here. So tracing these out, there's a component, and there's the other component. And the thing to notice about this is, again, I used red and black. Previously, this is what the 2x4 looks like. If you look at the first question, these are exactly the two colors, exactly the shape of the two components. Adding the square, basically, if I kind of cover up that dot and this dot, right, two of the dots of that square extend the red component, and then the other two dots extend the black component. It's nicely balanced so that each path starts and then ends in the same place. Let's do a couple others here. So this would be the monolinear. So this remains monolinear. Again, noticing that there's a piece right here, because the 2x2, remember, the 2x2 is a bilinear loose Sona. It has two components. So it might be surprising that adding something with two components onto something else doesn't change the number. We added two components to this 2x4, and we still have two components. So we had 2, and we got 2. Here we had one component. This is a monolinear loose Sona. We add two components, we get one component. What if we add it on the end? This you can kind of predict, because now this is 2x6. The greatest common divisor of 2 and 6 is 2, so we would expect this to have two components. There's one. There's the other, still two components. Here's another one. So there's that W component. Now, it's a little different than up here in that we extended two separate paths. But the key in all of these is that adding the square snips these paths, but when you leave this, you return to where you began. So you're not ending up somewhere else. You're starting and then finishing in the same place. This is a 2x5. The greatest common divisor is 1. So we would not expect anything but monolinearity, and that's the case. That's still monolinear. And again, notice what's happening here. This piece here is an extension of this, and then there's a separate piece over here that's an extension of this. As these paths enter this 2x2, they're not mixing. It's actually quite good that the 2x2 has these two separate components. And let's look to see what happens when we add a bunch of squares. Here I added a 2x2 on top, another 2x2, and then a further 2x2. So really adding a lot of complexity to these. So what was it, I think, oops, something like this. All right, there's an upside down V shape. Now we'll do oops, I might have made a mistake here. This should be monolinear. Right, because that would, oops, that's the mistake. I made a mistake back here. This should not have bounced. So this should have gone up and around. I missed the part. All right, there we go. So still only two curves, two components here, because again, we can see this black curve is extended here, and then it's extended here, and extended again. Each 2x2 square is just extending kind of like a lobe or a loop of a path. But they're still separate. I think this will probably be a three-part series. All right, let's yeah. Still monolinear. I think in this video what I want to do is I'll do these 4 examples, and in a separate video I'll talk about this. I will talk about this in class too. This exercise is about trying to prove something in general about squares, or getting that that thought started. Because there's some evidence that the Shokwe understood adding squares. There's one. And there's the other one, so that's still 2. And then this isn't going to be too surprising, right? We have 1, 2, 3, 4, 5, so this is a 5 by 3. What did I do over here? I think I said something wrong. Yeah. This is actually a 5 by 2. This is a 6 by 2. So this is just a straight rectilinear grid. No surprise there. Let's carry this one out. So of course the idea is that this will allow you to kind of compare your work, and if you need to pause the video and break down the steps. There's, again, it's two curves, quite lengthy curves, but still 2 curves. And then so still monolinear. All right, I think I'll break there.